All right. Well, thank you everyone for joining us today for OPWA Connects session. Just a little bit about the OPWA. We're a not-for-profit organization of public works practitioners, and we're the Ontario chapter for the Canadian Public Works Association and the American Public Works Association. We have over 600 public works members working with governments, municipalities, consultants, utility companies, contractors, and suppliers. Our branch is set up with the Central branch, as well as the Niagara region and an Ottawa Valley branch. So we'd like to welcome everyone, both members and non-members who are joining us today. And we'd encourage you to visit our website to learn more about our organization. We also have a number of committees and opportunities to become involved and work with other public works professionals. The mission statement of the OPWA is connecting the public works community. So this session today is an example of our Ontario Public Works Connects, which is a program intended to help our membership connect with educational and technical resources, as well as other webinars. We are having these about once a month, so we encourage you to keep in touch and check our website for more information and to find out all the different and exciting topics that we're continuing to have with these webinars. And with that, I'll introduce our speaker for today. So our speaker is Rob Sinclair. He has over 45 years of experience in hydrogeology, geothermal systems, soil remediation, water and wastewater treatment systems, and solid waste management. Rob is a senior technical advisor to the environmental department at KGS Group, where he previously served as the manager of environmental services for the Winnipeg, Thunder Bay, and Regina offices of our KGS. Rob Sinclair also has significant experience training students to manage and operate water treatment plants in Canada, as well as in Kenya, where he was a department head for water technology at Western College, and also as the department head for the water resources engineering technology at the Kelsey Institute in Saskatoon. Rob Sinclair holds a Bachelor of Science in Geological Engineering, a Master's of Science in Hydrogeology, and a Master's of Science in Environmental Engineering. And actually, just before Rob gets going, I did forget to mention, if you have any questions on Rob's presentation, please add them to the Q&A box and the chat function. And at the end of the presentation, we'll go through the questions with Rob. We are also recording this presentation, and this presentation will later be available through our website for your use. And with that, I'll turn it over to Rob. Thank you so much.
Thank you, Tricia. Okay, we'll get cracking here. Oh yeah, here, this thing. It's not moving. Okay, this is the presentation overview. We'll have a look at what is understanding geothermal energy. What are the components? Ground source heating systems, thermal energy storage options, which are very important, and geothermal system development steps and economic overview. This is the geothermal map of North America. It gives you an idea of the temperatures in the ground below, about 5 meters all around. Down where you guys are in Ontario, we're down into that, what, 9, 10 range. We're in the 6 range here in Winnipeg. Okay, geothermal facts, energy facts. Solar energy, yeah, it's stored a long time, hundreds, thousands of years, is a large source, but we find that it's certainly not an infinite source. There's been a lot of failures of systems because of overuse, taking too much energy out. It takes a long time for this energy to get in the ground, and it takes a lot less to take it out. So thermal balancing is a serious requirement for this thing. And many systems have failed because of improper or no thermal balancing. Geothermal systems can be cooling only, heating only, or both heating and cooling with thermal balancing. Open loop systems, aquifer based, are the most economical for larger systems based on rapid heat convection travel. Larger closed loop systems generally have poorer economics due to the large number of ground loops and space requirements as a result of the low thermal energy transfer. Soil cover is an insulator for open loop systems and a conductor for closed loop systems. Below about 5 meters, the ground temperature about 6.5 degrees the year round is in the Winnipeg area. Out in Toronto, 9 degrees, Thunder Bay and Winnipeg, 6.5, Florida, 20. We do quite a bit of work in the north, and up in Gillam, it's 2 degrees. And if you go further north, it's ice. Geothermal systems remove this stored energy for heating, cooling, and chilling purposes. So the components of a geothermal system, we've got heat pumps and chillers. Basically, and with that, there's the loop configuration. We have a few standard systems, and there's an open loop, which, as I say, I've got a couple of examples in this presentation of a couple of large open loop systems. So there's pumping and recharge wells. Vertical closed loop are drilled. Horizontal closed loop, which is probably well, certainly when we're looking at horizontal loop, using directionally drilled boreholes is the best. This excavated, I've been trying to fix some of them. They're not really working all that well. And we have surface water loops where they put them into the thermocline in a lake, and it's down in the 4-degree water. It works, but it's not particularly efficient. So when we're looking at geothermal systems, looking at thermal balancing sources, certainly surface waters are some of the best. Rivers, lakes, ponds, swamps, solar ponds are a new one that we've been looking at. Water has such a high intrinsic heat that it transfers a lot of energy very quickly. We also use natural warm and cold air using a fluid cooler, and sometimes we'll use a heat pump to boost it. The closed loop systems will be using HDPE pipe, high density polyethylene, and PEX. PEX piping for if we're collecting heat below, say, asphalt or soil areas that can get fairly warm. Solar panels, solar equipment are another source. A little more money, but there are folks that are using panels. Solar walls have come into vogue where you can blend it into the architecture, and it doesn't cost a lot of extra money. And also, there's always waste heat. Wastewater treatment plants have a lot of waste energy that can be used for a variety of different uses, heating and greenhouses, whatever. Heat pumps. Okay, the heat pumps, basically what they are, they're a mechanical device that moves energy. Doesn't produce energy, just moves it from one source to another. Works on a refrigeration cycle. A refrigerator, your refrigerator is a heat pump. Air conditioner is a heat pump. Heat pumps can both reverse and to cool and heat. Can be used to replace both boilers and chillers. Some standard heat pumps right here. The one in the middle at the top there is basically one I use for heating my pool at home. But the one on the left is one that we've used at Ikea. You'll see some of that later. Here's the size you can get of heat pumps, and this isn't even the biggest that's available. There's some bigger ones available in Europe, but this is one that's used in False Creek in Vancouver. So they're using this to take heat out of the wastewater and pump it through a whole subdivision or area of high-rise apartments. So these are the different heating systems that are available. These are just schematics, but you can see there's a closed loop horizontal. The best method for that right now is using directional drilling. Some of them are are just excavating these things into 8-10 foot trenches and putting in the piping, but horizontal directional drilling is pretty well made it the best for the closed loop systems. The vertical loops are okay too, but one of the things that's a problem with them is that there's so much plumbing. Every single borehole has to be connected in and feed the system. The horizontal ones you can do things like go under parking lots, or you can go under football fields. You can do things. They're drilling in horizontal loops up to 500 feet long and even a bit longer. So there's some of the vertical loops, 30 to 100 meters deep, based on a grid spacing of 4 to 6 meters. So you're seeing that's with that sort of spacing, that's about the travel distance that you're looking at in the ground by conduction. So it's not great. It's traveling half of that distance from each one. So they require a significant distance, certainly, or significant areas, especially if you're looking at the vertical loops. There's less and less of these going in. It's more and more of the horizontal boring loops where they can have easier connections and a lot less disruption to an area. So the horizontal loops, there's a variety of different ways of doing them, but in this particular one, we're showing a radial pattern where you can actually be at one location and shoot out using a directional drilling, and you can do it in layers. So you can space them out about 15 feet in depth, and you can go out. Some of these drillers now can do up to 60 feet deep, so you can get in a fairly compact area, get a pretty good volume of dirt that you can use for collecting heat, or certainly and also adding heat. This is one type of loop where you use a header system, and you can again drill down at 15, 30, 45 feet and end up with a fairly compact system, but a lot of area, or a lot of volume of earth to connect your system to. There's a surface water system as well. I've never put one in. I've had people ask me about it, but they are functional, but they are a problem, or the efficiency is not the greatest, because you're usually looking at the thermocline in the winter at 4 degrees C or lower. So it does work, but it's down the list of priority. This is one from Winnipeg, but this is just to show you some of the temperatures you're looking at, and out your way, you're even getting warmer. But if we're looking at this one here is, I think, the Red River in Winnipeg, you can see we're getting up into that near 25 C in the middle of summer. So there's a range in there if you're looking at anything along a river where you can get it fairly economically. There's a lot of available heat in a river. This is a pond we have out in Winnipeg as well. So we're looking here at getting temperatures well above 20 in the summertime. And this is a few acre pond. In fact, this was an old quarry pit, and these are the temperatures that they're collecting out of that. This is a fan coil. This is a job that you'll see a bit more later, but this is a methodology to collect heat. This particular one is one that I put in at the Manitoba Hydro Dorsey converter station. It's actually used for winter chilling, but you can reverse them. You can do them both ways. The winter chilling is more efficient than adding heat, but still they can be used summer and winter and the same unit. You can also use something like this, and this particular one is a heat pump, and they put them in order. They're small. This is actually a pool heat pump, and you can put them in. They're about $5,000 each, and over the summer, these things can put a whole pile of heat into the ground if you're looking at, and you can put it in with some of your I guess off-peak power too. You can put this stuff in the ground and have it for the winter heating. I haven't put one of these in, but it's certainly an option. This is what the Europeans are doing in a few areas. They're actually putting in this PEX piping underneath. In this particular case, they're taking it out of a major highway system and putting it into apartment blocks along the route. And it certainly would work, certainly down your way and here, putting this into a parking lot, etc. We haven't done anything with the roadways, and actually I have never really done one with a parking lot, but this is an option that the Europeans have been using for a while. There's also this one where you can either plow it in, and it's just basically PEX piping or even just HDPE into a grassed area to make yourself a solar collector. You can put it underneath a soccer field or a football field or any open field. These are sort of your hot water solar panels. These are some pictures that I took of someone when I was in China a few years ago. They have them all over the place in China. I wasn't going to put this one in, but I decided to do it. These are fairly inexpensive solar panels. I have them for my pool, and they're pretty. I have both the heat pump and these things to heat it, and they're pretty efficient. And they're down to about $5 a square foot for panels, which is fairly inexpensive. Solar walls. These are fairly new. They're basically made of aluminum, and they basically absorb heat, and they have air running through them. So this particular one, you can do in the summer, you can actually run this heat back down into the building through the heat pump system, and have this extra heat pumped right into the ground for your winter heating. And also it supplies some heat in the wintertime. A very large number of these are actually only used in the winter. 90% of the heat's wasted by not taking it in the summer and sticking it in the ground. This is something not really new, but it's called a solar pond. And really what it does is it can collect solar energy, but by putting in the salt zone in the bottom, it doesn't turn over like a normal pond where the water comes to the surface, evaporates to keep cool. This one doesn't turn over, so you end up with waters that get up into the 70 to 90 degree range. There's been one tested in Alberta, I think, but it hasn't really caught on. But I think it has some pretty good potential. It's fairly inexpensive, and we definitely have a lot of waste salt out here, certainly in Saskatchewan with all the potash mines. A couple of systems now I'll just go through with you. The open loop system that we put in for Ikea, one for Manitoba Hydro at their Dorsey converter station. What the converter station does is, in Manitoba, we have most of our power systems are all up north, our dams. So we convert to DC to come south, and then AC to distribute. So where the Dorsey converter station, it's the converter that takes it from DC to AC, and it produces a lot of heat. So they've been using massive amounts of chilling power and chillers to work all summer long, and they've got a fairly busy crew to look after it, and their maintenance costs are fairly high. So they were pretty happy with being able to eliminate their chillers totally. The cross lake loop closed loop system, Cross Lake First Nations. This was one where there was a spill from a fuel tank system, and we were hired to dig it out and put a soil farm together for it. And we talked to ISC, Indigenous Services Canada, and talked about potentially putting a geothermal system in the bottom of the hole and heating their building. And ultimately they said, okay, let's go for it. So we've put sort of a design together for them. Now this is the geothermal system for Ikea. The building's 400,000 square feet. We're pumping somewhere in the order of about 2,000 gallons a minute year round. And we have a set of pumping wells and recharge wells. The building itself is thermally balanced. With the way Ikea runs their business, they have lighting that never turns off. So you've always got that lighting going in. Even in the winter, you're getting heat. They have a fairly large staff. They have a large kitchen as well. They're always selling their Swedish meatballs. So they've got a pretty big kitchen, and there's a lot of customers there. And the heat pumps themselves, they put a little bit of heat in the building. But ultimately, when you do the balance on it, this thing didn't need any extra heat through the winter. In fact, we're finding now we've done some modeling on it, and we're seeing the temperatures actually go up a wee bit in this one. It started off at about 6.5, and it's nearly 8 degrees C now. So this is the setup. We've got 4 wells at the back, and it goes through the building, through the heat pumps and back out again. And we have 8 I think 8 recharge wells that we put all the water back in again. So we don't really have any consumptive use of groundwater. We strictly just borrow it. Few of the pictures of what a well. This is the well, one of the wells at Dorsey. We're doing a pump test on it there. That particular one, we were using an airlift system. It's an open loop, and there's 20 feet of clay on the surface. There's 4 supply wells, 8 recharge wells. They've got a gas boiler backup that hasn't been used. To start with, the design was actually going to be closed loop. Ikea brought their team in from BC to design geothermal for this facility and decided on putting 350 boreholes below the parking lot. And the contractor that was hired to build this contacted me, and I suggested maybe that when you connect up 350 boreholes under a parking lot in Winnipeg, that most of the heat's going to go to keeping the parking lot warm and not much in the building. So we switched over to a closed loop system, and now we've got 60 feet of clay for insulation instead of 4, and we're able to heat and cool with very little difficulty. They haven't really had any much problem with it. These are the heat pumps that they put in. These were the originals that were put in for the closed loop, but we modified it. There was some difficulties with space. Ultimately, I think I had to use a broom closet to get the plate and frame heat exchanger in. It's another one we've done. We completed for Manitoba Hydro. It's a similar system to Dorsey where you're recycling. This particular one though was strictly for cooling. They have a great excess of heat because of this AC/DC conversion. So in the summer, what we do is we take the water from the ground in that area and pump it through coolers inside the building, and it's about 7 degrees, and we pump that water out into the recharge wells back a few hundred meters from this. And then in the winter, we go through, I better punch a few here. Yeah, so you can see there's the winter chiller on the right. This is some of the drillers that were putting the wells together for me here. So we have a peak flow of 3,000 gallons a minute. There's 5 supply wells, 10 recharge wells. We did win an award for this particular one back. It's a fair number of years ago already. I think it's 16 or some years ago. The Dorsey system adds cold into the aquifer in the winter to balance all the heating. So in the summer, when we bring up 6 or 7 degree water, we actually pump it back in the ground at about 10. And in the winter, then we add cold to balance off the 10. And so we're putting 2 to 4 degree C water back in the ground, just using we got lots of cold air in Winnipeg in the winter to make air conditioning. This is the plate and frame heat exchanger. Pretty small. It's surprisingly how much water can go through these things. But anyway, yeah, we're not pumping 3,000 gallons a minute very often. It's mostly down into that half that range, 1,500 to 2,000. So this one, what it does is it allows you to take the heat and move it from one side to the other. So you can actually, so you take the cold on one side of the plate and it chills down the warmer stuff on the other side of the plate. These are the chillers that were in place, and there was about, I think there was 8 of them, and they're 100-ton each. And now these things on their own were, they produced a lot of heat, a lot of noise, fairly expensive to run, pretty high maintenance contract. And with hydro, they had to have these things running 24/7 in the summertime. So they had at least 2 to 3 people that were working on maintenance for them. So there was a significant salary involved, and it was a few $100,000 a year for just salary for these guys to look after this and maintenance. Plus Train had a maintenance contract. They weren't real happy with me when I got rid of this system for them. They don't speak to me much anymore, but anyway. This is the system. So you're pumping up cold water or cool water up through the air handling units to cool a place down, and then the warm goes into the ground, and then we reverse it in the winter, and same direction, but now we just take this winter chiller and use the plate heat exchanger and put cold back in the ground to balance the heat that we put in the summertime. This is a small system that we put together for Cross Lake. So basically what we did there, and I think I mentioned it, we excavated a hole for this contaminated site, and we ended up, that we haven't put it in, we're going to do it this summer, but the design we have is using slinky units. We were trying to make it so that the band could do a lot of the work, and the slinky units were quite easy to put in the ground and connect. And after that, you basically have to cover this with a good bed of sand and keep it saturated. All these systems in the ground have to be wet to be efficient. If you end up with any dry soil and pipes in them, they're nothing more than an insulator. You don't get much heat transfer at all. This is the inside of the facility. It's about, what was it, 170 feet long and about 60 feet wide. And there's one piece of the design we have is to put a solar wall on that particular face. And there's another stretch just a little further down for another solar wall. Another thing we want them to do here is we're looking at the field when it's finished, and we're going to end up with some granular on top, and we're going to tar it so that we can add heat in the summer, use that hot black heat going into the ground as a thermal balancing system, and then in the winter we're going to have them put blow snow all over the top of it to, again, give you some insulation in the winter time, keep that 40 below air from getting down into your system. So this is one of the efficient systems that we've used in that can be used. This particular one, it's called, they have them as a hot side cold side system. So in this particular one, you could have you've ended up making a little bubble of cold water. So you pump that out to your air conditioning in the summer up and through a heat exchanger to cool the building down, and the warm water will go into the ground. And so you've got a warm side that you've made, and you've got the cold side. You make your cold side or your warm side in the winter, and you take out the warm side in the summer and the cold side in the winter. So this would be one similar to what we've done at Dorsey. So to get rid of the chillers completely, it's just strictly a groundwater cooling system. And this is the reverse. We end up, with the warm side, we put it into the building through a heat exchanger and then through a heat pump to cool it down and do the heating in the winter. We'd like to cool it down as much as we can, and then we put it back down into the ground. And also as an add-on, just before it goes in the ground, we put a winter chiller on it, which is similar to that fan coil that you saw there, that big one. So we chill this stuff down into that 2 to 7 degree range. So we're ready for next summer for the air conditioning. And I think most of you know that, in terms of this, the chillers are one of the big expense. It's a lot more work and a lot more expensive to maintain than a boiler. But a heat pump system does both. It will both remove, does both heating and cooling. So you can see this system, depending on the one you want to do, if it's cooling side. But if you're looking at adding cold in the summer or in the winter, you can do more than just building cooling. You could use it for hockey rinks or refrigeration plants, anything like that. If you can get 2 to 7 degree water out in the summer when it's 35 out, that saves a lot of money on your compressor system and wear and tear as well. This is a horizontal boring unit. So this is one where there's their little bit in the front. It's a duck shoe type. Anyway, these guys can really horizontally drill, and the efficiency and ability to move the pipe and measure where it is surprising. They can they can drill 500 feet and come up within a few feet of where you want them. So when they're doing their drilling, I think I got one next here to show this a bit. So this is how we put in. This is a horizontal well system. So we drill down and we move to the far side and drill underground. We connect on then to a, typically it's a piece of poly pipe. Let's say we're gonna, well, we can put a 8-inch poly and pull it through. And then we slide into that hole, we slide a 6-inch PVC screen. And then beyond that, we pull out the poly, and now we've got a well screen in the aquifer that we can put pumps in both ends. We could put in submersibles in both ends. We could put in a end suction centrifugal in either end, but you end up with a well that, you know, it could be fairly poor aquifer, but if you can get 500-600 feet of open screen in that aquifer, it changes a lot. You could be getting 25 gallons a minute well and bump it up to, you know, the 500 gallons a minute kind of thing. I put a couple of these in. I put them into sand in Terrace Bay, Ontario. We put one in there to, actually what they were doing is putting in a sewer line. And so we put the horizontal well under it to dewater it for them. And they just left it in place. If they have any problems later, they can pump it and bring the water levels down. And also these drillers are pretty slick now too. They can go down 60 feet. They can go right. They can go through a bedrock aquifer now. They can go into some poor limestone, for example, and drill a hole and leave you with a well that, instead of, as I say, doing 20 gallons a minute, can do a couple of 100 gallons a minute. So this is when you see the bit emerges from the end. They put on one of them Chinese finger locks and pull the poly back down through the hole. In this particular case, they show you this U-bend. The U-bend reel, what it is that in one hole, the water goes back and forth in the same hole so that you can have all your connections to the building quite close to the building. So you've got, in this particular case, it looks like two 2-inch lines. They're stuck, they're welded together and have a U-tube at the end. But these things can come back to one location so that ultimately your plumbing is pretty simple to sort out. I go too far. Okay, this is sort of the steps that we look at to develop a geothermal system. One of the first things is the cheap energy, or the cheap information. We look for the drilling data, the geologic reports, even talk to drillers. From your current heating load, you can do an assessment of your seasonal heat load analysis. How much is cooling, how much is heating, to give you an idea how you design your geothermal system. You can do some modeling too. We have models for the open loop system called FEFlow, and for closed loops we use COMSOL. But it gives us an opportunity to kind of work out and do some estimates of how much piping we need, etc. And also, I guess at that point, an economic overview is part of what certainly the owner would do, is take a look at what their costs are for these different for heating and cooling, and the operational costs of chillers and boilers, and determine what's going. Gas is pretty cheap right now, so it is in some cases it's difficult to bump it out of the place. But I guess if they start charging for greenhouse gas emissions, that might change things around. So then we go to test drilling and pump testing, just to have a look at what your conditions are on your site, to make sure that we understand what we're looking at, whether we have to go vertical wells, horizontal wells, or horizontal closed loop. And with that data, we may do a little more modeling, and then we look at final system design and construction. So we drill the wells, we do the mechanical piping, electrical installation, and then we finish up with the commissioning. It's basically the steps that we put together for Ikea and Dorsey. There's other smaller ones that I've done too for apartment blocks, etc. that I didn't put them in. There's I got too many slides as it is. I think I got to get cracking. This is the Europeans now. This is the way they look at geothermal energy. But you can see at the top, their most economic is aquifer thermal energy storage systems, or aquifer systems. And then there's borehole. In our case, certainly you could use vertical, but also horizontal. Then they have the ground loops vertical as the third to fourth. And now they've got this COP on there, that coefficient of performance. And what it means is that if you have a coefficient of performance of say 8, it means that if you put in $1 of electricity, for example, you get the equivalent of $8 out. So as you move down through the system, you get down to where you're into resistive heat, and you're basically at 1. That's what you're getting, a COP of 1, which means you put $1 in and you get $1 out. I put this in just for interest's sake for you folks. There's a number of these gone in where they actually embed this stuff in the bridges and actually use it to melt the ice in the wintertime. I'll show you, there's an example here of one from down Southern Ontario in Essex County. So what it does, it removes the ice and snow. You can start it when a snowstorm starts or whatever, you can start it up remotely. The cost of salt corrosion is a big deal if you can eliminate that, and also the salt that's running off. So you can actually, in a lot of cases, you're crossing water, so you do have a whole blast of thermal balancing water right underneath you when you're doing it. Not always, but often. You can raise the temperature in the ground. There's also the piping that they put into the bridge is actually like that PEX piping is similar to it's a solar collector, so it's collecting heat in the summer and putting it into the ground and adding to it for the winter. Most of our bridges are built, so there are some retrofit options where you actually put the piping under the bottom of the slab and then put spray-on insulation to keep the temperature and push it through the bottom of the slab. Not quite as efficient, but if you're looking at, if you've got an aquifer or something underneath, it might be something that's worth looking at and saving adding to the lifespan of the bridge. This is one that they've done in Lincoln, Nebraska. Here's one in Essex County, Ontario. I've never seen it, but I was looking at some of the information from it. So they've got this in place and are able to keep that road clean and not have to use a lot or any salt actually. And here's one last slide from it's an old guy in just north of or just south of where I live in Winnipeg, and he's got a geothermal greenhouse down near War Road, and it's called, you can't see the citrus that clear, but it's called Citrus in the Snow. So it's some stuff with food security for greenhouses. And we're finding now that there's a fairly large demand. We have a number of projects that we're looking at with the federal government for First Nations to develop greenhouses that can produce food in the north. There's a serious problem with different types of food insecurity, and certainly there's a pile of things. We're actually looking at one with Manitoba Hydro where we're looking at some waste heat there at one of these converter stations, and actually looking at trying to build a couple of greenhouses that can use the waste heat. They have in one, well, the one I was looking at, like 1,000 gallons a minute of 100-degree Fahrenheit water that goes out to that winter chiller that you saw there and just dumps the heat into the air. So we're looking at trying to take that energy and grow food up in the north. So the geothermal has a variety of different applications. Okay, I think that's my last slide here. Any questions? I guess that's something you'll work through.
Great, thank you very much, Rob. It was very interesting and educational presentation. If you do have any questions, please add them to either the Q&A or the chat functions on your screen. Right now, we do have one question on the bridge retrofit slide that you showed us, and that was on the bridge retrofit, could that be installed in the waterproofing system if that was being rehabbed? This person, their waterproofing is typically 90 millimeters, including the board and the asphalt topping.
Yeah, I think so. Yeah, you know, anything like that would work. I've talked to a number of folks that are looking after bridges, and they're always concerned with putting this on. But they're also looking at you know, if you look at an asphalt overlay that you could put this into. So there are ways more than just going underneath it. If you're looking at something where you could put an asphalt overlay, you could put this in similar to a new bridge design.
Okay, great. Again, if you have any questions, oh, I see we have another one here. Are there issues with using open loop system if the aquifer is used for your drinking water supply?
If you're putting the system in properly, no, there's not a lot of concern for it. You know, you try to keep it a bit away from it if you could, but no, in some cases, they actually take the domestic water supply pumping system and use it as one of the wells in a geothermal system. So if you properly design it, it's not too big a problem, but you have to be careful the way you put it in. But you certainly, it's not an overriding concern.
Okay, I had a question myself. So when you're looking at using geothermal, is there a different type of ground system that would be better? Because you did mention clay is a good insulator. So would you be looking for a lot of clay or a big aquifer? Like what would help tell you that a geothermal system would work well in this application?
Typically, if you have an aquifer there where you can go through and check to see with drillers and well logs and see that you've got an aquifer there, or if you know the locals are got domestic wells there, but if you can get an open loop system put in, the economics are quite a bit better than closed loop. It's not to say a closed loop doesn't work, but it does take a little more effort and a little more money to put in the piping. One of the things that, you know, I've been thinking about this too much for too long, but one of the things on the cooling side is that if you put in the winter, you could actually, well, there's been some problems with geothermal systems, closed loop, where without thermal balancing, they start to freeze up the pipes. They actually take so much heat out that the ground around the piping starts to freeze. And so there's been situations where some of that thinner piping has actually collapsed. But I've been thinking about it in terms of the chilling side. If you could do a little bit of freezing around some of these pipes, if you were putting it in a closed loop and did a little bit of ground freezing around it, you get that heat of fusion that's, well, in the old school, 144 BTUs per pound. So automatically you can get pretty close to a open loop system if you can put in something that where you in the winter freeze and put a block of, I don't know, really, that's one of the things that's a little questionable is how much we could do, but I think you could put a foot or so of ice around these pipes and still have it and put in a heavier grade of poly in the ground and end up with a system that can do some pretty good air conditioning. In fact, if you get water coming out of there at somewhere in that, well, you could actually put it down below zero, but certainly you could do some good chilling for any kind of rink. And I think there's a limit. You can't get into the huge systems, but you certainly could do some decent sized cooling with a system where you could freeze it a bit. As I say, there isn't a lot of experience with it. It's been mostly negative experience where you find out that it's frozen.
Okay, we do have another question. On the systems with the body of surface water, so a lake or river, there was some slides noting a rise in temperature around 10 degrees Celsius. Would there be any pushback from the fisheries agencies on trying to keep the cold water bodies cold?
There could be. As I say, I took that one out and I've never done it. I find that it's not the greatest. It has some cooling potential, I guess, for air conditioning. But for myself, what I've been using these for, or taking heat out of a river, for example, in the summer, is actually to load up a ground loop system. I've got a few folks that are interested. I'm looking at one right now up at it's an RCMP new facility up at Barons River, which is First Nations, and they've got the Barons River nearby. So that's one of the things we're looking at, is just basically taking water out of the river. As soon as it's above the ground temperature at Barons River, which is about 5 degrees, once it's above that, the plan is to pump water through this thing at 100 or 200 gallons a minute, and just take that heat, put it and fill up the field over the summer. And then basically the water, the way you pump it, it pumps in through the field and then back out to the river downstream. So we are looking at them as certainly an opportunity. And yeah, we do have to watch the fish end. When we put a pump in, we have to have a proper screen that meets DFO requirements.
Okay, we have a few more questions coming in. So another question we've got is that this person has been asked to consider installing closed loop systems under a road during the reconstruction process. What would the challenges be for that?
Well, you could drill them in after you finish construction. I would suggest that, depending on the geology, that it would be, you'd want to go deeper. Normally, the shallowest you want to go with these things is around 15 feet. If you get some of them, there's one I'm looking at for a school in northern Manitoba that the system is frozen up and broken about half the pipes, but they put it down in these excavated trenches down 7 feet, and it's just not working properly. They never did thermally balance it either, so that was a problem. But I think if you were, I'm not quite sure what you want to do under the road. Is it to collect heat from the asphalt, or is it just? I guess I'm not quite getting the drift of what exactly you want to do. If you want to collect heat from the asphalt, you can certainly go under it with that PEX piping that they've used in Europe. But otherwise, you could horizontally bore it wherever you want below the road.
Okay. Another question we have is that this person, they're considering a system on a residential building lot where it's surface bedrock. Would geothermal be a viable solution with surface bedrock?
Well, it is. I mean, I've done a bit of chasing around, because we have a lot of sites in northern Manitoba too, where we have Precambrian rock at surface. And I've chased around looking for drillers. I mean, the typical was, where they just send out a well driller and you'd say, well, $35 a foot, I can drill to 500 feet, whatever. That was just way out of control. Excuse me. So I have chased around, and now I've talked to a few quarry drillers, the folks that have those pen drills, and they blast down holes and then they blast out rock. So they're actually, I got a pricing from one of them there that was $7 a foot to drill me a 20-meter hole, 4 inches in diameter, that we could use for geothermal. So that's getting into the range of being economic. But it really comes down to is you've got to get a driller that I would suggest that normally you're not going to get much of a pricing from a well driller or from anybody that's doing coring, mining type drilling. You're going to have to try somebody like a quarry guy that sits there and just pounds holes down and blasts faces off walls. And those are the guys I went to, and I think there's an opportunity to do it. I've not done it, but I tinkered with it.
Okay, another question that we have, do you have much experience with using waste heat from sanitary sewers? So I guess I've kind of a little familiar with waste heat from sewage treatment plants. I'm not sure if there's something similar with the sanitary sewer system.
Well, there is, yeah. There's a few systems that they have where they're taking heat out of the sewer itself. It's a little trickier. There's a lot of, you got lumps and stuff to wrestle with, but yeah, there are systems. I think you could check on the web for it, or if you send me an email, I can dig some stuff up that I've looked at already for that. But certainly the wastewater, taking heat out of wastewater plants is pretty big deal in Europe, and it's getting more of a job here too. And it has the benefits of taking the heat out and putting it into the river at more closer to ambient. Plus you've got heat now to heat the building or heat whatever you want. Or as I say, you could have a greenhouse at the end of the sewage plant. I think we're at a time now that we've got to start looking being a little smarter with what our energy sources are. If there's any of you out there that are actually looking at a new or an upgraded wastewater plant, you could send me an email. I've been working with a concept on actually using heat pumps to beef up the system. In a nutshell, what I'm looking at is that if you look at that huge heat pump that was at the beginning there with the heat removal for False Creek in Vancouver, if you think about whether you could just take that same system and now instead of putting the heat through all of the apartment blocks, is put that heat back to the front end of your plant. So you take that heat and you warm up your influent and get the plant heated up. So there's it's an interesting concept. It's not as if I invented it, but it was invented or pulled out of the blue about 30 years ago by some Russian guys, but they never did do it and never have done it. But the concept, I think, is pretty solid. And you can take, I did some modeling on a system using heat pumps. I had a pretty big outfit in Winnipeg, EH Price. They did some modeling for me on a plant, I don't know, population about 20, I think it was 500 gallon a minute plant. Anyway, within 2 or 3 days, we could take water at 8 degrees and take the heat out before it hits the river and recycle it to the back and actually warm the plant up to, we had it up to 26 degrees in 2.5 days. So it's something I'm looking at. I've put a few papers together on it, but I haven't really, if anybody out there interested in has a plant that they're looking at some upgrades, it'd be interesting, even just to start with a pilot system. But I think the theory is pretty simple, but it hasn't been done.
Okay, another question we have, what is the mechanism of having the heat above the ground in summer transferred and stored in summer and used in cold winter, as you mentioned during the presentation?
Well, basically, you're going to have a fan coil. I mean, part of it would be, well, you'd have a fan coil on surface or one of those other surfaces, you know, the rivers, the creeks, the air. But a fan coil is usually the easiest. It can be done in just about any area. So you end up with a fan coil that you pump your water through that and raise the temperature during the summer and put it in the ground. It's not quite as efficient as using water out of a creek or, you know, river or whatever, but it is an alternative that can be used. The fan coil system is best for cooling, just because of the gradients we're looking at. We can get temperatures in the -10 range that you're trying to cool a building down to, say, 70 or 20, I guess. So that gradient is reasonably easy to do because you can store the heat in the ground. It's difficult to get heat any higher in the ground for heating. Basically, you need something in the range of 30 degrees to get enough gradient through a heat exchanger to get 20 in the building. But there hasn't been any much work done on that side of it. But there are certainly a number of ways of putting heat in the ground in the summer. The heat pump system that you saw with those pool heaters is another. They're very efficient when you're looking at a COP of 7 or 8 means you're putting heat in the ground at a cost of 1 cent a kilowatt hour instead of 8. Does that answer it somewhat?
I guess in terms of the cost savings, because the whole intent, I guess, with this is that it saves cost. Do you have an idea of how much that Ikea facility is saving in heating and cooling or anything?
They're pretty tight with their numbers, but they've been, I think, when we first started looking at it, they were able to reduce their heating, cooling. IKEA's got the green thumb. They want geothermal just about under any circumstance. So they were willing to spend the money to put it in, as I say, on 350-foot boreholes down to 60 feet. So, but the economics are pretty good, and I think they can keep their. The problem is with Winnipeg, we got cheap gas and cheap electricity, and that kind of is it's a little difficult to jump over. you folks are getting a little higher electric bills, and would make more sense out your way than us. But still, it's a simple system for them, and they don't really need any much maintenance, and they're looking down the road of what would happen if we start getting charges for greenhouse gas emissions.
Okay, and with the closed loop vertical, I was a bit curious because you have both pipes, like one going down, one going up. Do you just install it in a very big well? And if so, like what diameter do you need to install those pipes in?
They're not that big. No, we're typically drilling them down. It could be as small as 4-inch pipes, and we end up. What we do is we put those U loops in, so one goes down and up. So you can see that when you get to ground surface, you got every single borehole has 2 pipes coming out of it. So you got to get one connected to the in and one connected to the out, and so there's a pretty massive plumbing job if you've got. In the case of Ikea there, they were going to have 350 connections that they had to make, and they were going to be approximately 4 feet below the parking lot, which is pretty frosty in Winnipeg in the winter, as compared to the folks in BC that thought it was not a bad idea. Anyway, it is a lot more plumbing. The horizontal directional drilling has replaced a lot of that vertical stuff where you can basically go in 3 layers and keep on the ends or edges of your property and just make connections in along one header on either side and not have to tear the parking lot totally in pieces. I wouldn't put in a vertical loop system myself if I could, unless it's the last resort kind of thing. How are we doing for time?
I was just going to say it's coming on to 1 o'clock. So I think with that, we've heard some really interesting questions and had a bit of a lively discussion. So I think that's been very useful because this is maybe a technology that's a bit new to us, or some of us anyway. And this has been a useful presentation to see some of the examples and how it's being used in Europe. So with that, on behalf of OPWA, I'd really like to thank Rob for his time and expertise in presenting to us today. His contact information is there, so if you have any other questions that have yet to be answered, I'm sure Rob would be happy to answer them if you shoot him over an email. So thank you very much, Rob, and thank you everyone else for joining us for our workshop today.
You folks are welcome to send me anything like that, any questions. I'm open to it. I only work part-time now that I've turned in. I'm 72, so I don't work full-time anymore. So I got time to answer emails.
All right, that's perfect. Thanks so much, everyone, then.